thank you so much for showing showing the initiative and participate in the physical launch of our class. I believe within the next 30 minutes or so, we'll have more people coming in. And thank you so much for signing up for this class itself. I promise you it will be a very life-changing experience for you guys, where you get to learn a lot of functional programming, learn how to deal with Cardano and build smart contracts on their platform. Yeah, and who knows, opportunities lay ahead for you. So we as African Blockchain Center, we have partnered with the Input-Output Global team, which is the main team that develops the Cardano blockchain as well as other platforms and the smart contract platforms as well. So we are highly honored to host you guys for this training course. Just to let you know, we'll be having this, for the first 2 weeks, we'll be having these sessions running physically here. And also they'll be recorded because we have participants also who are not within the country. We have participants all across Africa, so that they're also able to catch up and learn with the rest of the participants. We'll learn a lot. There'll be a lot of very good, interesting information you get. And the IOG team, I'll now pass it over as well to the IOG team to proceed with the program. Yes, but I hadn't mentioned my name, I think. Did I mention my name? Also, for those who have been receiving all my emails, I'm Anderson Rioba. I'm the knowledge manager for Africa Blockchain Center. So I'll pass it over to the IOG team. So Lars, welcome.
Okay, so I'm Lars Brunjes. You can call me Lars, of course, and I'm the director of education at IOG. So I've been with the company for more than 6 years, I think, almost from the beginning. And my background is in mathematics, so I have a PhD in mathematics. And I first joined IOG as a Haskell developer. So Haskell is the language that we will spend lots of time in this course learning. And then, my mother was a teacher, so I always had an interest in teaching. So when the opportunity arose, I taught a Haskell class in Athens, and then later on Barbados in Ethiopia. So I've done one course in Africa before. Then Mongolia, but that was when COVID hit, so that Mongolia course was virtual. And now, after COVID, this is the first one we do again. So the other ones were all like 2 months in person, but for this one we chose this hybrid solution. So we will be here, the three of us, for 2 weeks, and then the rest of the class will be virtual. Okay, so maybe my colleagues can introduce themselves. Robertino.
Hi, I'm Robertino Martinez. I joined IO around a bit more than a year ago. I'm also I'm an engineer, not a mathematician. So I've been coding with Haskell for forever, and I tried it after coding for almost a decade in OOP languages, and it was like, why just now I learned about this? So now I'm like super happy to share it, share the gospel with everyone. So yeah, any questions you may have, feel free to ask, like to interrupt us, and now and through Discord and whatever, we're here for you. These 2 weeks live, and then these other 6 weeks online. So we'll be there for you. Please do reach us for any doubts and whatever you might need. Karina?
Hi, I'm Karina. So I'm computer science. So, I'm in IUG more than the 2 years. So, but I only want to share. I only want to say that I hope you enjoy the course, and feel free to research us, and we are happy to help. I'm here only for 2 weeks, but then we have the contact virtual, but is the same. Like we are here. Okay. Yeah.
Thank you, Karina. And we should, I mentioned this Mongolia class in 2020. So that was virtual, and therefore Karina, for example, also could join, even though she's Mexican.
Yeah.
And she worked during the day and attended the classes at night and was one of the best students. And now she's working with us. So, so there's the success story right there.
Thank you.
Okay, so I think we are maybe a bit many for every single one to introduce themselves. So maybe I'm just curious, how many of you are like professional software developers? Maybe a show of hand. Any? Okay, that's a lot. And students, like university students? Okay. And has any of you any experience with Haskell? Nope. One. Two. Or functional languages, other functional languages? Like Clojure or OCaml or ML or PureScript? Rust. Okay, no, that's fine. And blockchain, any blockchain experience? Okay, oh, quite a lot. But I assume not with Cardano, maybe Ethereum or Cardano? Cool.
Nice.
So you can do part of the course, you know, Haskell, you know, Cardano. Okay, so course schedule, I think we must see how it goes. I mean, I can just say the previous courses were all full-time, like 40 hours a week, full-time, 2 months, very tough. So a lot of students told me that was the toughest course they ever did. But I mean, if you manage to get through, it's certainly worth it. So now I hear from Anderson that some of you or most of you like have commitments in the morning, so we can't do full-time, I suppose, only afternoons. Right. Yes. So we must see how it goes. But I think for now the plan is that we start at like in the early afternoon.
Yeah,
like
try to be very early. At least by 2.
Yes. And then at least for the first 2 weeks we will have lectures every day and then exercises, and we must see whether we have time to do the exercises together here or whether you have to do that at home. Depends. Right, yeah, so let's see. Introductions we did, schedule I mentioned, sort of. So now, I mean, we will start with lectures, everyday lecture, and then the first week we have small exercises, so basically daily after each lecture there are some exercises, and then later we swap to a weekly rhythm, so we have like more difficult ones, but then only once a week for that week. And I think it's not mentioned there, but we also have tests, like small tests that we want to do the first one on Friday this week, and then every 2 weeks, just for us to be able to see, I mean, how you follow the class and where there are problems and where we should re-explain something. Okay, and today, so this is now the welcome lecture, then I have a short lecture, Introduction to Cryptocurrency, so most of you, or a lot of you probably won't need that because you already have blockchain experience. Then we start with Haskell, an overview of Haskell and what makes it special and unusual. And then hopefully we still have time that Robertino can quickly walk you through how to get started. So we have several options, 2 online options and 1 Docker-based local option. And you will get your first set of small assignments. So like with everything, I mean, related to programming, it's important that you actually do it. I mean, just listening to lectures is not enough. I mean, it's important to practice it. Because often one listens to something and thinks it all makes sense and you understand. But then if you actually have to do it, it's a different story. So it's important that you keep writing a lot of Haskell in the next 2 months. Okay, and then, as I say, I mean, everything here is fluid and up to discussion, and we must just see how it goes. But, so the idea is that these first 2 weeks, we basically have daily lectures, and of course you can always ask questions and interrupt me, and we can discuss, and I try to come up with examples if there's the need for it. And then when we leave Kenya, then I think we will have like 3 lectures a week, and then the other 2 days more for exercises and questions. For like the first 6 weeks, or anyway, and then in the end, so this is all Haskell, like the first couple of weeks are all Haskell, and then in the end we come to specific Cardano smart contracts that you need Haskell for in order to do that, and then we might change the schedule again. I think then it's like daily lectures again for this smart contract part. Okay, let's see. So full-time course, as I said, I mean, it used to be 1, but we must just see how much time you can invest. And of course, as I just said, I mean, it's important that you actually do the exercises and the assignments, because otherwise it's impossible to learn a programming language if you're not writing code. And please ask questions. I mean, in this Ethiopia course, I told Anderson yesterday, it was a bit difficult in the beginning because it seems in Ethiopian culture, teachers are like authoritative figures and students are not encouraged to ask questions. But Anderson assures me that Kenyans are different and very inquisitive. So I have high hopes for this. And you can also suggest ideas, or if there's something you want to learn more about or something different, feel free to suggest it. And the whole setup is flexible. So I think in all my previous courses, we changed something in between, like different days for the lectures, or more lectures or less lectures, or whatever. I mean, we must just see how it goes. Right. And I already mentioned this, so the first week is different. There's like daily assignments, but then, is it Friday, did we say Monday? I think this week we will wait until Monday for the first weekly assignment.
We can send it on Friday so they can
start looking at it. But there's at least one problem in the first weekly assignment where you need next week, Monday's lecture.
Yeah.
But maybe we hand it out on Friday already, so you can get started with the others. Yes. And this electronic submission thing, so we use GitHub Classroom. We use that for Mongolia as well. I must confess, I also forgot how exactly it works, but it's very simple for you. So you basically click on a link and then you get your own private clone of the repository containing the assignments, and then you can like push your solution, and then we see it and can grade it. Yeah, right, and you can work in teams if you like, but we believe that more than 4 people is less efficient, because then there's at least one that doesn't do anything. So, okay. I mentioned the test, and those are individual tests and very short. I mean, if you are like a Haskell expert, you could solve them in like 10 minutes. But you will get more time, of course, but they are very simple, just to check the basic understanding. And right, then we have some project assignments, like larger projects, like infrequently. So the first come after a few weeks. And there you can work in the same teams that you use for the assignments. And we will talk about details and like milestones later. And then in the end you can demo or should demo your outcomes. And I don't know whether we have a slide for that, but for this course, because Anderson told us a lot of you are very eager to like solve real world problems of your communities. So we want to, I mean, you will be able in the end of the course to like develop your own D-apps on Cardano. And then we thought that in the last week you can work on your own projects, and we can still see the details how that goes, but yes, so there should be time for you to work on something that you yourself are passionate about. Right, and then there may be additional stuff that depends how it's going and how curious you are, that we read some papers maybe, or extra challenges, or maybe invite a guest lecture or watch a video together, and the final project that I just mentioned is on this slide as well. Okay. And communication, so Anderson just set up a Discord for us.
Yeah, I'll share the Discord. So how about Telegram?
Right, maybe we can.
The link is in the repo, so we will share the repo after the lesson.
Yes. So we have a GitHub repo for you where all the slides will be in and all the assignments, everything. And then we can put the Discord link and Telegram maybe. Okay. So you're right. Stack Overflow you can use for questions and discussions. I mean, you can ask questions on Discord as well. We will try to answer. We also have like quite a big team in the background back home. So it won't just be the three of us. So there may be more people that can help answer questions.
They are all over the world, so you can ask anytime. Yeah.
Right, and GitHub. So we will mostly use GitHub for distribution of materials, assignments and lectures and links and so on. Example code. Okay, that's already it. So that was the welcome lecture. Are there any questions at this point to me, to us?
Something you want to share with us?
Okay, if there are no questions at this point, then we can dive right into the short introduction to cryptocurrencies. But it's really just an overview, and it's anything but complete. And we will, I mean, whenever you need something in more detail, we come to that later when we talk about. I mean, there are some assignments later where you're supposed to implement certain aspects of a blockchain. And then, of course, when we talk about smart contracts. So this is just like a teaser for blockchain. And maybe after this lecture, we can have a short break or something, depending on what the time is. And then there is one more lecture for today, an introduction to Haskell. Okay, so we just want to briefly talk about what blockchains and cryptocurrencies are and how they work in principle, and about IOG, but I think very few words about IOG and about Haskell. Yeah, these days you have to be very careful with what you say. Okay, I mean, these slides are very old, but there's a quote from Wikipedia. Blockchain is a distributed database that's used to maintain a continuously growing list of records called blocks. Each block contains a timestamp and a link to a previous block. I mean, I always, these days when I talk about blockchain, I use a different picture. I always talk about the ledger in the sky. So ledger is this old-fashioned thick book where people make entries one after the other. So for example, like in Middle Ages or so, banks, I mean, there was somebody sitting somewhere on a market stall, in a market stall, and had this big book. And then if you want to send money to somebody in a different town or so, you would make an entry in this ledger. And this is fine as long as you trust that person that maintains the ledger. But even if he's trustworthy, there are problems with that. I mean, it's a book made of paper. So if there's a fire, for example, then all the records are gone. Or whatever, a flood, or it can be stolen. And then, of course, yes? Oh, am I too energetic?
Put it back. You put it on the back side.
Oh, so I mustn't sit down.
Yeah.
That's what you're saying.
No, you will. When you're ready, tell us.
Okay.
Yeah, good.
Thank you.
So he will have to hold at some point, so you'll have to drop the microphone. Is there some way so he can speak directly to it or something like that? He will have to draw. It's like something I put with the headset or something.
But that's okay. We can still get
That's okay?
back. Yeah.
Okay, so
Okay.
This one is just for the
okay.
Right. Okay.
we have the sound.
Okay.
Perfect.
Okay, good.
So we don't give this for more people.
Yeah, right.
Mhm.
Otherwise, they could have used them.
Okay. Right, where was I? Ledger in the Sky. So there's this book, and I mean, it worked good enough, well enough, but I mean, there are problems. As I said, it can be like fires or floods, or it can be stolen. And then, of course, the person making the entries can be a crook, and he can cheat, or it can try to delete it afterwards or manipulate it. So there are certain problems with it. But in principle, as a data structure, it's very useful. So the main property of such a ledger is, I mean, you can make entries. They are like in linear order, one line after the other. and you are not supposed to ever change them again or delete them. So it's like a write-only memory. So it's not like a normal database where you can delete and update and so on. I mean, in this ledger, the point is you make one entry after the other, one follows the other in a linear order, and once it's there, and you can't manipulate it or delete it. And I mean, this is not useful for any problem, but for some important problems. So one important way where ledger is useful is finance, sending money from A to B. So I mean, there you have these entries. Each entry is a financial transaction that somebody sends some amount of money to somebody else. So there it's very useful if you have such a ledger. Other examples are, for example, property deeds, if the ledger entries are who owns what property. And for cases like that, it's useful to have this ledger. But as I said, it has these problems, fire, fraud, whatever. So what blockchain tries to do, it tries to give you this data structure, this ledger data structure, but in a secure, decentralized way. So you don't just have one copy of a book made from paper that can burn, and you don't have to trust one single person like this banker making the entries. Instead, you have thousands, millions of copies spread all over the world. So it's secure from fire and flood. And as long as the majority of the people maintaining these copies of the lecture are honest, you can tolerate a certain amount of crooks and frauds and criminals. And then I mean, it has very nice properties. I mean, it's secure. You can't manipulate it. All these things we said that a ledger ideally should have, that you can't delete entries and so on. That's what blockchain gives you. So for these examples, I mean, like cryptocurrency, if you do financial transactions using blockchain, then it's called cryptocurrency. And then, I mean, you have these properties that you can't, in retrospect, manipulate entries or say, no, he didn't send money or he sent a different amount or to a different address and so on. And for property deeds also can be very useful, because then you can't have a corruption, for example, to manipulate who owns what property. When I taught this course in Ethiopia, I also had 4 Ugandan students. I don't know, is anybody here from Uganda by any chance? Oh. So they told me, some of the students told me that there were big problems in Uganda with property that, I mean, there were corrupt governments or corrupt local governments, and then often somebody had to buy his own house or his own property several times because the records were made disappear. And then the governor or whoever said, no, you don't own that, you have to pay again if you want to live there. And that's one of the things where blockchain can help, because it makes it impossible to manipulate such records. But I'm the first one to say that blockchain doesn't solve any problem, so every problem. I mean, there are lots of cases where run-of-the-mill old-fashioned database is much more suitable than a blockchain. Because blockchain, for example, because of this thousands of copies, and all the thousands of copies carry the same data, so it's a massive waste of space and computation. So you pay a high price for these guarantees of security and decentralization. So you can't solve any problem in the world, every problem in the world with blockchain. But for these use cases like cryptocurrency or record keeping, property deeds, supply chains, it's very useful. So maybe now that I talked so much, most of that I already covered. So it's write only in the sense that, I mean, of course you can also read it. What I mean by write only is you can't update or delete or edit entries. Decentralized, so you don't, it's not a single point of failure. So you have massive replication of the data. So no matter what natural catastrophe or war or civil war or whatever happens, there are always copies elsewhere in the world. And I mean, you also get private blockchains, but when we talk about blockchain here in this course, we mostly talk about, or only talk about public ledgers. So there everybody has access as well. So nobody can stop you going on Cardano or Bitcoin or Ethereum and running your own node and doing transactions. So financial transaction I mentioned property rights. Another use case is diplomas. So So that goes into the digital identity direction. We had this UNet thing. It's an old prototype or experiment we did some years ago with Greek universities. So they had this little private blockchain, I think 8 universities, where all the students' diplomas were on that, and then you could share it with like employers, for example. A much more interesting one is like an outcome of my course in 2019 in Ethiopia was that our company did a deal with the Ethiopian government, so they are busy putting all their high school students' grades and diplomas on the blockchain. And then the idea is that it's easier for somebody from Ethiopia to, for example, go to California and apply for a job, because then he can use the blockchain to prove that he has this degree. So that's another use case. Okay, and I already said so, but okay, according to Andy Greenberg, whoever he is, cryptocurrency, digital asset designed to work as a medium of exchange using cryptography to secure the transactions and to control the creation of additional units of currency. Right, I want to go a tiny little bit into cryptography. None of you needs to become a cryptographer, but I feel it's useful to at least know some basic building blocks to understand how this all works. And cryptocurrency, so as I said, it's the blockchain, it's this ledger specialized to the special case where the entries in the ledger are financial transactions. Somebody sending a certain amount of whatever currency to somebody else. So the ledger entries are transactions, and normally you identify yourself with so-called public key. So it's like your address. I mean, on Ethereum you have that as well. And I mean, it gets more complicated when we come to smart contracts, but basically every person has like a public key and a private key. Only he knows the private key, but the public key is, as the name suggests, public. And if you want to send money to that person, you basically send it to his public key. Right. And if you know the private key, you are in control of the money associated with this key. So it's very bad to leak your private key, because then people can take your money. And so this is like the most basic functionality that you expect of a cryptocurrency, that you can send money from A to B. But on top of that, there are more things that cryptocurrencies normally offer. For example, like conditions, under which conditions can you mint new coins, or maybe you can create like your own tokens. Cardano, for example, has something called native tokens, where that's very easy and like built in. Ethereum famously has this ERC20 stuff. Then, I mean, all these thousands of so-called nodes, copies of the ledger, have to be operated by somebody, and those people need a reason to do this. And some do it just because they believe in the idea, so idealistic motives. But it's more solid and reliable, of course, if they also get reimbursed somehow for their efforts. So there's also something like transaction fees and rewards. So if you run a Bitcoin node or an Ethereum node or a Cardano node, then normally the operator of these nodes that help like maintaining the blockchain, they get rewarded. So there are transaction fees, which are typically much lower, at least in the case of Cardano, much lower than like bank transfer fees. But nevertheless, there are some fees, and they get then distributed to the people that maintain the blockchain. And yes, we will talk a lot about smart contracts, which allow you to basically codify certain rules, how transactions should go in code on the blockchain. Okay, so let's talk a little bit about why a blockchain is called blockchain. So in this image of the ledger of the book, I talked about the entries, the lines. So in that image, a block would correspond to a page. So a page in a book doesn't really have any meaning. I mean, often you get a reprint of a book with a different number of pages, where they just, I mean, it's smaller pages and more pages then, or bigger pages and you get fewer pages. So it's just a way to group the lines, because, I mean, if we are not ancient Egyptians, we don't want to write all the lines on a long scroll. I mean, we bundle it in books. And with blockchain, it's similar. So each of these blocks just bundles a certain number of transactions, but that doesn't really mean anything. It's just a convenience thing. You don't want to deal with every single block transaction on its own. You bundle them, and that's called a block. So in the book, that would correspond to a page. You have a number of lines on a page. And it's called a chain because ideally it should look like this. So it starts somewhere. So there's the first block that's called Genesis block, like from the Bible, Genesis, beginning. And then there's a first block and a second block, and each block references the block before it. And so all the blocks together form a chain. So that's what it should look like, or how you can think of it. And it's like the pages in the book, right? In the book, the pages are not just in a box, loose pages. I mean, they are bound together in a book in a definite order. And this is very important if you think about it, for example, financial transactions. I mean, if you have, I mean, it matters, order matters. I mean, if first I send 1,000 ADA to Robertino and he sends 1,000 back, that's different to the other way around, especially if I have for example, if I have only 500 ADA, then he can send me 1,000 and I can send 1,000 back, but not the other way around because I don't have 1,000 to begin with. So order with transactions matters. I mean, so like for a story, if you want to read the story, it's important that you get the pages telling the story in the right order. And it's the same in blockchain. And I said that already. That. Okay, and then of course the question is, how do you make this safe? So for example, how do you prevent that somebody forges a ledger entry or manipulates it or tampers with a block, like exchanges one block for another? And that's where one important cryptographic building block comes in, so-called hash functions. They are all over the place in blockchain. And a hash function just takes an arbitrary byte string, but I mean, it can be in principle anything, like picture as well or whatever, anything you can serialize into bytes. It can be arbitrarily long. And the hash function is a function that takes such an arbitrarily long blob of data and maps it to a fixed length byte string. So for example, 256 bits. Was it bytes? SHA-256, bytes. Right, and it can not just be any old function, it needs certain properties. So you should, because it's all over the place and you permanently have to compute hashes, it should be effectively computable, so you can compute the hash fast. Collision-free means that it should never happen that you have two different documents that have the same hash, which of course, if you have any background in mathematics, is impossible to achieve, because if you think about it, there's an infinite number of possible potential documents, but there's only a finite number of potential hashes because it's fixed length, right? I mean, it's a very large number, but you only have like a limited number of possible hashes, but you have an infinite number of possible documents that you want to hash. So of course, there must be a collision. It's in mathematics, we call it the pigeonhole principle. If you have 10 pigeons, you can't fit them into 8 holes without 2 at least sharing a hole. So it's the same thing here. So what collision-free means, it should be just very highly unlikely to find a collision. So historically, there were hashing algorithms, I think MD5, where people actually did find a collision. So they found 2 different documents that have the same hash. But I mean, we try to use for blockchain, we try to use algorithms where it's practically impossible to find 2 documents that have the same hash. I mean, mathematically, theoretically, it's guaranteed that there are infinitely many that have the same hash. But in practice, it should be impossible to find that. And hiding means, given the hash, it should be impossible to reconstruct the original document. And puzzle-friendly is not really important for Cardano. It's more important for Bitcoin and Ethereum. But it's very similar to hiding. So it means that it should be difficult to find an input that has a predefined hash or a hash with a certain property, like in the case of Bitcoin, like a given number of zeros in the beginning of the hash. Right, and once you have such a hash function, you can do interesting things. We come to that. The second building block is that's important for blockchain is digital signatures. And there are many of those, but it doesn't matter. The details don't matter. So what you need is, first of all, you must be able to generate a key pair. I mentioned public key and private key before, so that's like also what you need for a digital signature, private key, public key. I say private and public, but this P is for, it's public, but the S is for secret. So you can also say public key and secret key. And then you must be able to sign. So if you have a document and you have a private key, a secret key, then you can sign that document with your secret key, and out comes, again, something that looks like a hash, so a short fixed length byte string. And that's your digital signature. And then for people to verify a digital signature, so given a document and the signature and your public key, then without knowing the private key, they must be able to verify that it's indeed your signature, so that only the owner of the secret key could have produced this signature. And yeah, there are well-known algorithms for that. Right, and it should also be infeasible to guess a valid signature, obviously, because then you could just make up, guess a signature. So it should only be possible to sign if you have the secret key. Right, and now, what does that have to do with blockchain? So these ledger entries all have to be digitally signed. And by whom depends on the context. But in the simple case that I want to send 1,000 ADA to Robertino, it's my money, so I have to sign it. So I wouldn't just, so in this book, it wouldn't just say Lars is sending 100 ADA to Robertino. It would also have my signature. And then, of course, in the digital case. And then we have these blocks. So, there's more technicality, but every block is, in addition, signed by whoever created that block. So somebody collects all transactions, bundles them in a block, and signs that, and that's how it creates a block. This is not really, it doesn't have an analog in the book example, because normally book pages are not signed by the printer, but would be that. And that means that no matter what else, nobody can steal your money. Because each entry, if it says Lars sent 1,000 ADA somewhere, it must always be signed by me. So if you believe these properties here, that there are algorithms that do reliable digital signatures, then it's safe. Nobody can steal your money. In order to steal your money, somebody would need to be able to forge your digital signature. So that's one important thing. And then to get this block structure, we saw on this diagram the links that always you link to the previous block, and that is achieved with hashing. So you have a block and you hash that block basically, and then the next block contains the hash of the previous block. So you always say, okay, my previous block has the following hash, and that guarantees that this chain is you can't manipulate the chain. Somebody tried to insert a block, then the hashes wouldn't make it work out anymore. So this combination of hash and digital signature basically guarantees that we get something like this, where the blocks can't be afterwards manipulated, and where each entry is guaranteed to be signed by the person that controls the funds for that. Okay, so that is, and all of this was actually solved in the 1970s, I think. But we still only got Bitcoin in 2008. So what was the problem? Why did it take 30 more years to get cryptocurrencies? And that's another problem, and that's called forking. So in reality, it doesn't look like this. It looks more like that. So it's not a chain. It's actually a tree. Because people are asynchronously all over the world trying to build blocks, and you somehow can't prevent that. Let's say block 0, 1, and 2 already exist, and now people want to create the next block, and it will happen that two people basically try to build a new block, and they both reference this one, and then what you end up with is something like this tree. So the big problem is how do you prevent it, or at least if you don't prevent it, how do you achieve that these so-called forks, because it forks like a fork in the road, that they don't become too big. Because you somehow, I mean, the point is you must know the true history, right? If you think of transactions, you could imagine that here in this block, I send, I don't know, 10,000 ADA to a car dealer and buy a, not a Lamborghini, but let's say a scooter. And here is a transaction where I take the same 1,000 ADA and buy a new laptop, right? So now it's important, I mean, it's like two different views of reality. In one, I bought a scooter, and another, I bought a laptop. So it's important, of course, to know, I mean, it doesn't matter which one. I mean, both is fine. But somehow we must decide which is the true reality and which not. And it doesn't matter which we pick, but somehow we must pick. And all people in the world that run nodes, that have these copies of the lecture, somehow must decide. And this is called consensus, I mean, to agree or reach agreement. So that was the big ingredient that was missing for 30 years or so until Bitcoin came along. Because this Bitcoin algorithm, the proof of work algorithm from Bitcoin, was the first one that gave an algorithm that makes it possible to make this decision. So an algorithm to, if you are in a situation like that, pick this one or that one. It's not guaranteed, it's completely indeterministic which one will be picked, but one of them will be picked. And all the nodes will agree on that one. And then continue building that one that was picked. So in this case, people would now not try to make the chain longer here, they would try to make the chain longer here. So this can still happen, but it will be short. It will be like 1 or 2 blocks that dangle off the main chain, but most will agree on what the main chain is and try to make that longer. And this algorithm is called consensus, as I said. And there are several, but the first one was the one from Bitcoin. Right, and I explained this already, so it's important that everything is nice and ordered. And these forks are bad because that's so-called double spending. So I could use the same money and spend it on 2 different things. And that, of course, is not what we expect of a currency. That's exactly what you don't want of a currency. Right. And it's not possible to prevent these forks. I mean, even if nobody tries to cheat, if you just think of like a global network like the internet, and it could just be that the transatlantic cable between Europe and the US breaks, I mean, it can happen that some parts of the world become isolated. So there's no way, they don't know what the other part does. So they don't know whether a block already exists that prolongs the chain. So it can happen. Even if nobody is of ill will, it can happen. And so somehow you need a protocol that in these situations eventually like decides for one of the 2 forks and everything can go on. And that's, as I said, it's called a consensus protocol. And one important property is, so you can never have this thing that you have this beautiful picture of just the chain. But what you can have is something called common prefix. And that basically says after throwing away the last k blocks, where k depends on the blockchain and on how sure you will be, every copy of this ledger is the same. So if we go back to this picture, it could be that some people that run a node have this view of the world, so they have these 5 blocks, but somebody else has a different view of the world. It has these 5 blocks. So for some people, maybe they believe I bought a scooter, and other people believe I bought a laptop. And this common prefix now says, if we drop like the newest 2 blocks in this picture, then everybody will agree. So it's like in this book, the first, I mean, all but the last couple of pages, everybody agrees on the beginning of the book. Only in the last couple of pages there can become some disagreement. And that is fine. And this is the reason, if any of you have ever done like transaction, Bitcoin, or bought something on an exchange or so, they always make you wait for an hour before you can access your money. And that's for exactly this reason. So they wait until, I mean, this hour in the case of Bitcoin, it's just a rule of thumb, but it's like 6 blocks. And on Bitcoin, you have on average 1 block every 10 minutes. So on Bitcoin, basically, what is 2 in this diagram is 6. So if you drop the last 6 blocks, you can be very sure that what you get, everybody will agree on this. The last 6 blocks, they can be different opinion, but everything before the last 6 blocks, everybody in the world agrees. And that means if you wait an hour, so you wait for 6 more blocks, then everything before those last 6 blocks is like set in stone. And that's this common prefix property that Bitcoin has, Ethereum has, Cardano also has. Right, and the idea, I mean, if you wonder how is this achieved, this consensus protocol, the very high level idea is that somehow the right to create a new block is tied to some sort of asset that mostly belongs to honest people. And what this asset is, that depends on the blockchain. So in the case of Bitcoin and Ethereum, or at least the old Ethereum, it was hashing power, computational power. So they have these mining. I mean, Bitcoin works. You must solve these so-called hashing puzzles. You must do a lot of computation, and your chances of solving these puzzles are higher the bigger your computer is. So the asset in this case is like hardware, computing hardware. And I mean, the trick is to have a limited asset. So the total computational power in the world is limited, and therefore that works. And the problem is that, I mean, proof of work, it works, but it's very costly. I think the cost of running the Bitcoin network is something in the order of magnitude of running a medium-sized country like Belgium, electricity-wise. And people were willing to accept that because they said, well, it's worth it because you get all these nice features like decentralization and so on. But there are alternatives. So Cardano, that we work on, was the first so-called proof-of-stake blockchain that did a different thing where we don't have this waste of electricity. By now, there are several proof-of-stake blockchains, and I think even Ethereum swapped recently. But we were the first, at least. And there, it's not computational power. In proof of stake, the asset that regulates consensus is stake in the cryptocurrency itself. So our cryptocurrency is called ADA, and the more ADA you have, the higher your chances are that you can create the next block. So you can think of it as a lottery. I mean, it isn't implemented like that, but you can think of it that, I mean, there are coins like the currency is called ADA, but one ADA is 1 million so-called Loveless, which, by the way, I should mention. So it's named after Ada Lovelace, which was in the 19th century, I think, a woman. And she was, I think, girlfriend or friend of Lord Byron, the poet. And she was the first programmer in the world. And not just female programmer, full stop. So the first programmer in the world was a woman called Ada Lovelace. Unfortunately, they didn't have computers back then, so she did it like on paper. But I mean, her friend Babbage, he tried to construct the so-called analytical engine. It was like a mechanical computer. And I mean, he ran out of money, and at that time, the mechanical engineering wasn't precise enough to actually make it work. But later, now, some years ago, people actually took his plans and built it so it would have worked. And it was a programmable computer, so we could write programs, and Ada Lovelace was the first person in the world that ever wrote programs for that computer. So in her honor, we name our cryptocurrency Ada, and the small unit is Loveless. So 1 ADA, 1 million Loveless. So this proof of stake, you can think of it how it works, that every Loveless, so there's a certain limited amount of Loveless coins in the whole world, and you basically run a lottery, you draw randomly one of those coins, and whoever owns that coin has the right to produce the next block. Now, obviously, the more coins you have, it's as if you have bought more lottery tickets, the higher your chances are. So in our case, it's not linked to how big your computer is, it's linked to how many ADA you have. And I mean, it sounds horribly oligarchic and I mean unfair, But I think it makes sense because if you have a lot of ADA, you invested a lot of money into the cryptocurrency, which means you have a very high interest in it running smoothly. Because if something goes wrong and there's double spending, then ADA will crash and you will lose all your investment. So it sort of makes sense, I think, to have something like proof of stake, because people that invested a lot into the cryptocurrency also have a very big interest in it succeeding. And right. Yes, yes. If you try to cheat, you lose all your investment. Okay, I think I'm now just looking a bit more at what this ledger. I mean, until now I always said Lars sends 1,000 ADA to Robertino or something like that. It's, I mean, in reality, it's a bit more complicated. So first of all, you can have more than, I mean, several so-called inputs. I mean, we go into that. It's not important for now. We have an exercise later in a week or so where you are actually supposed to implement something like that in Haskell. But it's more, it's in Cardano and also in Bitcoin, it's less like a bank account and more like a wallet. So you have like several coins in your wallet, and in a transaction, you specify which of those coins you want to spend. So that's the inputs. And it could even be like different owners. So Robertino and I could also get together and say we want to send whatever 1,000 ADA to Karina. And so these inputs could, some could belong to Robertino and some to me, but then we would both need to sign the transaction, of course. So there can be inputs, then there can be several outputs as well. So you can, in the same transaction, send to several recipients. And because of this coin thing, often you don't have the exact amount in your wallet, so you need change. So typically one of the outputs goes back to yourself with the change. And then, as I said, so every input is signed by the owner of it. So for now, when we talk about smart contracts, that gets more complicated. Yes, so that's that. Right, and you always use inputs up completely. That's why you need change. So you can't, if you have 100 ADA coin in your wallet, and I want to pay for coffee 10 ADA, I can't just split that into 90-10. I must use the full 100 ADA and then create a transaction with two outputs. 10 go to the coffee vendor and 90 go back to myself as change. And that's the same in Bitcoin. So whoever of you has experience with Bitcoin, is the so-called UTXO model. So Ethereum works differently. Yeah, just a graphical example. Let me see. Okay, fine. So in this case, Alice and Bob together want to send 50 ADA to Charlie. So Alice has 42 and Bob has 10. So those are the inputs. So 42 from Alice, 10 from Bob. So if you add that up, it's 52, but you only want to send 50 to Charlie. So then 2 would be change. And in this case, for whatever reason, sorry. I'm sorry. Alice starts with 100, Bob starts with 10. So they put it together, it's 110. And in this example, so Charlie gets 50, Bob gets 2 change, and Alice gets 58 change, and the image is wrong. I mean, that this change should be from...
Alice put only 42 in the transaction.
Yeah, and yeah, but that is stupid. So forget the image. It's not my image, by the way. I took it from Manuel's book, I think, or something.
Okay.
Anyway, there are much nicer images elsewhere. We can swap that later, or you can draw if you want.
Yeah, you keep going.
Okay. Right, and I mean, as I said before, like there are these people that try to create new blocks and that they look for transactions floating around and bundle them in a block and put them into the chain. And before they do that, they check whether the transaction is valid. And there are lots of rules that make a transaction valid. So, but some of them are like all the signatures need to be verified. So if like in that example, Alice and Bob have to sign the transaction, and the person or the node that wants to integrate this transaction into a new block on the blockchain would check these signatures, whether they are valid. And if not, then the transaction is not considered. And then, of course, like the money must end up. So the sum of the input values must equal or be greater than the sum of the output values. And this is all like only mostly true because there are like more fancy things like minting new tokens and transaction fees, but just to get the idea. And then the whole block contains a list of transactions, and that the block is valid if whoever creates the block has the right to create it. So in what I said earlier with the lottery, so he must be a lottery winner in order to create it. And he must have, validly signed the block, and each individual transaction in the block must be valid, and they must all be consistent. So that's what I said earlier. So if I could create a transaction that sends 1,000 ADA to a scooter vendor, and that transaction would be valid, and I could have a second transaction that sends the same 1,000 ADA to a laptop vendor, and that transaction would also be valid. So each individual transaction is valid, but in combination they would not be, because if whatever is first, the second one would be invalid because it tries to spend the same amount of money again. So this is what's meant with consistency. So even if every individual transaction is valid, it doesn't mean that in sequence they are valid. Right, and these two, the first two items, are valid for any blockchain, also if it has nothing to do with cryptocurrency, for property or supply chains or diplomas, whereas the last are specific to cryptocurrencies. Right, and I alluded to fees already, so that depends on the cryptocurrency. But roughly speaking, if there's more input than output, then the difference is transaction fees. And that depends, I think, on Ethereum, for example, it's not set how much. It's more like the more you put in, the faster you hope your transactions get processed. In Cardano, at the moment, it's different, that there is like a fixed fee. It depends on the size of the transaction, but it's not that you put an arbitrary amount in there. And I'm sorry?
You know it beforehand.
Yes, you know it beforehand. On Ethereum, you always have this problem that depending on network congestion, the same transaction, if you send it now, could be more expensive than if you send it later, because right now the network is very busy. On Cardano, it just depends on the transaction, not on the time of day you transmit it. And then, how the fees are distributed also depends on the specific blockchain. So for example, in Bitcoin, the block creator gets all the fees. So in Bitcoin, the person that assembles the new block, you look at every single transaction in that block and you add up all the fees and he gets them. So that's one of the incentives why people are very eager, spend a lot of money building powerful machines to create Bitcoin blocks because they get the fees. But they don't only get the fees, they also get some called Coinbase, in the case of Bitcoin, like on top of the fees. Right, so that's that. And just briefly, right, about us, I think that's a little bit outdated maybe. But Cardano has like 3 branches. So it's us, IOG, then it's the Cardano Foundation and Emergo. And at least originally the idea was that we built it. The Cardano Foundation, interested in adoption, education, regulation, non-profit stuff, and Emergo commercializes it. So now it's more complicated in reality, but the basic thing is that we are like an engineering company. And we don't only do Cardano, but so for example, we also worked on Ethereum Classic. So there was a fork in Ethereum, and the one's called Ethereum Classic, and we did that as well in Scala, which is another functional language, or at least like a hybrid object-oriented functional. And Ada, which was developed in, Ada is actually stupid, it should be Cardano, but anyway, in Haskell. Ada is just a currency. And we have a heavy emphasis on academic research, and software developers. So we do a lot of publications. I lost track, but it's far more than 100, maybe 200. 140 at the moment, like peer-reviewed scientific publications like presented at proper conferences. Yes, committed to best practices. So in academia in particular, it means peer-reviewed papers. Software development, we try to get it right. We try to be very rigorous. So wherever possible, we try to mathematically prove our things. Sometimes, of course, that's, many of you are software engineers, so you know it's not always feasible to do like formal verification, but we try our best. So what can be formally verified, we do formally verify. So yes, we have our own formal verification team. So in that regard, we are like spacecrafts or aircrafts. But other things we just do like lots of testing. And Haskell is particularly well suited for testing. So we'll come to that next Monday, I think, if all goes well. Yes. And it's also sort of trying to not just build Cardano, but a bit more general, so that also other people can take part of our protocols or our code and build their own thing. So it's more like a toolbox for cryptocurrencies. And we always try to get things right without cutting corners, which of course, if you run a business, is not always easy. But we have been accused in the past of being too slow, and yes, but we try to get it right, even if it means that we delay a promised deadline sometimes. Okay, and Haskell. So why did we choose Haskell? So it has a very high level of abstraction. So it's like, in that sense, the opposite of assembly or C. So you talk on a very high level, which is good if you want to express complex protocols like consensus of a blockchain. Very expressive, very terse, so your code tends to be smaller, like less lines. And it's somehow particularly well suited for writing DSLs, domain-specific languages, like protocols or like smart contract languages, for example, Marlo, that we will see towards the end of the course. And because it's functional and declarative and pure, we talk about all those things in more detail, it's particularly easier than with other languages to formally verify Haskell code. It's still not easy, but it's at least doable, or more easier than with like Java. And it's statically typed, so which means that it's not like Python or JavaScript or TypeScript, that it's only at runtime you get the errors. You have a compiler, and the compiler catches a lot of type errors already before you even get to runtime. And a lot of people developers have bad associations with statically typed languages like Java because they get annoyed by the compiler. But in Haskell, actually, most Haskell developers see the compiler as their best friend, because the type system is so sophisticated and flexible that you can express a lot more invariants and things in the Haskell type system than, for example, in the Java TypeScript system. So the compiler can really help you write your code and write it correctly. It's not just annoying, it's actually helpful.
Kind of like Copilot.
Yes, like Copilot, exactly.
Another thing that the strong inference of Haskell makes it so you don't have to like write the types of everything like in Java or not other programming languages. You can just let the compiler infer most of the types and just declare the ones that can be confusing or can cause trouble.
Mm-hmm. Oh yeah, and it's fun. I think so. And I think, Charles Hoskinson, who founded, or one of the co-founders of IOG, who incidentally also was one of the co-founders of Ethereum, I think he picked Haskell, and I think he just picked it because he liked, not just, but he liked it. So yes, and I hope that you will share, agree that it's fun after this course. Okay, so that's the second lecture. There's a third one, Introduction to Haskell, but I would suggest we make at least 5 minutes break or so.
Anyone has any questions about hashes, protocols? We're going to go deeper than like the first 4 weeks is just Haskell, because Haskell is general purpose, so you can use it for web servers, like a bunch of stuff. So we're not going to go any deeper on the blockchain stuff up until the 5th week. But then we're going to go full on blockchain from the 5th till the end. So if you have any questions now, we can answer now. If you need to be like further explain, like develop a whole topic, we can do that in the final weeks.
Mhm.
So you will be quite. Um, you have a lot of Haskell work until then, so you'll have stuff to do. Don't worry. But any other questions, like specific questions about whatever I said?
Okay. I think we will break until, yeah, sure.
Yeah.
So my question is, so you said that the blockchain is
Mhm.
like a linear data structure.
Mhm.
So let's say you have maybe 10 power 9 blocks, and maybe you want to check the balance of say an address that the balance for an address that say it's in 10 power 6, the 10 power 6 block. Now when checking the address, now will it go by block by block by block?
In principle, yes, yes.
So it seems it's a lot of when you look at the 10 complexity space.
That's a very good point.
Yes.
I mean-
yes, like in the, sorry, you want to,
No,
because we have a thing for that, the indexers.
yes, I mean, so in theory, you would have to start at Genesis and then work your way through every single block in the chain until you reach the present time in order to figure out all the balances. So you have to really start at the beginning and go all the way up, which would be inefficient. And therefore, we have stuff like indexers. Like, I mean, theoretically, it's beautiful and nice, but I mean, in practice, it would be inefficient. So we have like additional tools called indexers that do that for you. So basically, that I mean, every single new block is like accumulated, and
You basically
yeah.
end up with an SQL database.
Yes,
works
that has all
super
the
fast. Yeah. So
Yes.
yeah, that's it. Yeah, each node has its own, like not the producers necessarily, but the consumers have its own indexer. So every time a new block is created, it's indexed in the database, and it's aggregated, and you can even have like specialized indexes for whatever you care the most.
Mhm.
And you can just when you query the blockchain, you just query the database.
So yeah, in practice, it's not inefficient. And in theory, I mean, it's nice because you don't have to trust any database. I mean, if I now start a new node, I don't have to trust Robertino's database. I can build my own one. I mean, it will take a while to start from like when 5 years ago when Cardano started, work my way to the present. And actually, we're working right now on something that makes it faster.
Yeah, my point.
We have like these trusted checkpoints where you don't have to start all the way from the beginning. But in principle, I mean, at the moment at least, it's still how it works. So if you run a new node, you start in the beginning. It takes a couple of days until you have synchronized. But then it's fine. I mean, then you have like your local caches and you know how much belongs to everyone, and you don't every time have to go back.
Most people don't need an actual node.
Right.
They just send the transactions to a service or whatever that can actually runs the node and performs the transactions for them. So it's just an API.
Any other questions? Yes.
I'm asking about the forgeries along the chain. Is it like impossible to have a security breach on the chain, or simply extremely hard?
I mean, not mathematically impossible, but we are talking about it's more likely that all the air molecules in this room decide to leave and we all suffocate. I mean, it's all it's all statistics. I mean, mathematically speaking, I mean, hashing, for example, I said before, pigeonhole principle, there could be hash collisions. Or digital signatures, I mean, you could like guess it. But somebody's. I mean, I could just have a very, very, very lucky guess and guess Robertino's signature or private key.
Yeah.
But in practice, I mean, it's like astronomically unlikely. So it's, yes.
Yeah. So there's like trillions of Lovelesses, and you have like, for example, for to game the blockchain, you should have like to be picked every time to create a new block, and you can just lie and keep lying because no one will check because you're the only one that produces the block. But for that to happen, like there's like the odds are so close to zero, like so many zeros before the point that is like virtually impossible.
Right, and I mentioned this hour before, so you can also, if you wait longer, you get more security.
Yeah.
So I mean, this hour is just a rule of thumb for Bitcoin.
We have like a couple of minutes.
Yes, Cardano is a couple of minutes, but if you are scared, then you can just wait like half an hour longer, and then
Yeah.
it's again billion times
Yeah.
more secure. So yeah, I mean, in principle, there is no, I mean, it's not 100, not really 100%, but it's 99 with so many nines that it doesn't make a practical difference. Right. So lists are particularly important in many programming languages, but in particular in Haskell, also for historical reasons. So they have special support in Haskell, special syntactic support. And they are incidentally very similar to this chain type we defined. So we had our chain type, it had one type parameter, and then two constructors, one basically to generate the empty chain, and then one for block, which takes an existing chain and a new payload and generates a longer chain with this payload added. And this is very similar to how the list type in Haskell is defined. So a list of elements of type A in Haskell is written like this. So this is like special syntax just for lists. Normally it's always, as we saw, I mean, type name and then type arguments. But in the case of lists, it's written with this angular brackets and the type argument is in the brackets. And we have two constructors. The one corresponding to Genesis block. The empty list is just two empty brackets. So this is an empty list. And then where we had the block constructor for our custom chain type, it's the colon operator for, it's called consing. So taking the head of a list and the tail, construct a list with this head and the tail. So if we have like this chain here as an example, another chain, which uses, so it's the Genesis block, then a 1 and then a 2. So basically very similar is the list that starts with a 2, then a 1, and then the empty list. And it's just the other way around. So, I mean, it's those types are completely, like in a sense, they are more or less the same type. But you notice here, in the recursive case, we first had the existing list and then the new element. And for the built-in list, it's the other way around. First the new elements and then new element and then the tail of the list. And there's more syntactic sugar for that. So first of all, the colon operator is right associative. So one can leave those parentheses. So you can also write like the second line. And there's even more support, so you don't have to write it explicitly like this, 2:1 square brackets. You can just write like square brackets and then list the elements. So we can, and actually that's also how GHCI displays it. So if I do this, I just tell it that it's an int, but so :1 empty list. If I evaluate that in GHCI, it displays it in this more compact way. But I could also just input that directly. So that's built-in lists. And strings in Haskell are just lists of characters. So until now we only saw the built-in types int and bool. So character is another built-in type, sort of, also the prelude. That's for Unicode characters. And in Haskell, a string is just a type synonym for a list of characters. So for example, I can do, character literals are written with single quotes. So this, maybe I should start with that. So if I ask for the type of this, it's of type character. So I can build a list. Like this. And this is just the string Kenya. And there's also syntactic sugar for strings. So I mean, I could write it as we just learned on the other slide, like so. But I can even just write it with double quotes. And these three ways of writing it, it's all the same. It's all the same list. But because strings are so common, there's the special syntax with the double quotes. But this is just a list of characters, which is not very efficient. So, I mean, we will later have a lecture where we talk about string types. So it's actually discouraged to use strings in your programs, except in special cases, because they are much more efficient and compact string-like types in Haskell. But this is like the easiest one. And it has special support, syntax support. Right. And there is, I mean, we defined this chain length type, but actually there's a built-in function, more or less built-in, called length. It works for all types that are foldable. And of course, you don't know yet what that means. But list is a special case. So foldable is another type class. We talked briefly about this EQ type class for things you can compare for equality. And foldable is for so-called containers. And list is a special example. So length works for more general things than list, but in particular for lists. So for example, because a string is just a list, I can ask for the length of Kenya, and I get 5, because it's a list of 5 characters. Right. So this length function, because it's polymorphic, it would work for a list of integers, but also length of a string. So, I mean, I showed you for Kenya for a string, and we can also do it for integers. We had this example here. So I can ask for the length of that, and it has length 2 as expected. Okay. Then there are other useful functions defined in the prelude for lists, or for more general for foldable things. The list is a special example. So lm, given you have a type that you can compare for equality, A, and some foldable container like lists, and given something of type A and, for example, a list of A's, you get a Boolean whether this A is contained in the list or not. So we can try this out with Kenya. So for example, we can ask whether Y is an element of Kenya, and we get true. But if I ask whether Q is an element of Kenya, I get false. And same, I mean, it would work the same for like integer lists. So 42 is not an element of the list containing 1 and 2, but 2 is. And I mean, there are many functions on lists in the prelude. We don't want to list all of them, but just some examples. So any checks whether, I mean, it gets, so this lm, maybe some of you will recognize, is very similar to our has block function. So our has block function was like a special version of lm for our chain type, which is very similar to lists. And then we had this has block prop function, where you can take an arbitrary predicate on elements and check whether in the chain there was a block with that property. And for lists, we have, this is called any. So it takes a predicate on elements and a container with such elements, like a list, and says whether such an element is in the container. So for example, I can, let me import data, no, let's, yeah, okay. Data.character, never mind, so I'm just importing a library where there are some functions on strings. So for example, we have is upper, taking a character and says whether it's an uppercase letter or not. So if I have if up is upper, capital K is true and lowercase k is false. And now I can use this, so for example, for any, so I can ask any is upper Kenya, and this is true because the capital K is in there. But if I this, then it's false because there's no capital letter in there. And it would also work, we saw this even and odd. So for example, I can ask any even in 3, 5, 7, 9. It's false. In the list 1, 3, 5, 7, 9, there is no even number. But if I put somewhere, I put an even number, then it's true. And as I said, those two are just examples of functions for lists or more general foldables. Another function is reverse. So we can reverse a list, which does what you would expect it does. If we reverse Kenya, it reverses the list, and of course it would also work for lists like this. Plus concatenates lists. So for example, we can do Haskell and it concatenates, but again it works for arbitrary lists, so we can also concatenate with 4, 5, 6 and get the concatenation of that. Filter, as the name suggests, gets a predicate and a list and only keeps those elements of the list that fulfill the predicate. So if I take this this example list again and do filter even, it will only keep the even elements of the list, which in this case is only one, namely 26. And if I do filter odd, it will only keep the odd elements, so it will throw out the 26. And map, I mean, that's also, I think even in JavaScript it's called map these days. For example, in this data character, there is a function called toUpper, which takes a character and returns a character, so it turns the letter into its uppercase version. So for example, toUpper small y is a capital Y. So now I can map toUpper over the list of characters Kenya, and I get it in all caps. So this is a function, the given function is applied to every element of the list, and then the list of the results is returned. That's map. Right, and then two very general functions, it for identity, which just returns the element you give us, and that works for any type. A can be whatever, there's no restriction on A, it works for anything. And const, it takes two arguments, ignores the second one and just returns the first one. So for example, I could say const, I don't know, Kenya false, and it just returns Kenya. So it completely ignores the false and just returns the first argument. And maybe you wonder why that's useful, but later in the course, I mean, there are plenty of examples where it's useful. Then there are, of course, all the numerical operations you would expect. We already earlier saw plus, then there is division, and equality, I mean comparisons, like this is less than or equal. And you see they all take like various type classes. So the num type class is for numeric types. So we saw ints, but there are many more in Haskell, like doubles and floats and arbitrary precision integers and like words of different lengths, like word 32, word 64, and so on. Fractional are types where you have division, for example, double. So And ORD is for types that can be compared, I mean, that have an order. So for example, integers are an instance of that. So if I have 1, I can ask whether 1 is less than or equal 7, and I get true. But character is also an instance of ORD. So for example, I can ask whether the character A is less than or equal the character B, and I also get true. But for example, Y is not less than or equal B. Right. And show. So there's a type class capital show for things that are showable. So that means they have a function show that takes an element of the type and converts it to a string. So for example, bool is showable. So I can say show true. And that, I mean, the way to show true is to give the string that contains the word true. And earlier, in the reason, I mean, right in the beginning when I had this chain 1, I got an error message, and that is because there is no instance for show chain. So our type chain isn't an instance of the show class, and therefore GHTI, whenever you ask it to evaluate something, it computes the result and then it wants to show it. And if it can only do that if the result type is an instance of show. And at the moment it's not, and therefore we can't look at values of our chain. But, okay, we come to that in a second. So this is just a list of important, I mean, there are many more types in Haskell, but those are quite important and appear frequently. So eq for things that you can compare for equality, or for things that where you can compare like the size, num for numeric types, fractional for fractional numeric types like double, show for things that have a string representation, read for the opposite, where you given a string you can pass it. So for example, bool is an instance of that, so I can say read true, the string true, and I want a bool back, and then I can pass this string as a boolean. Enum, it's like finite types. If you only have like bool is, for example, is an enum because it only has these two values, false and true. Bounded for types that have the smallest and the largest value. So for example, int is one because it's a fixed size int, it's 64-bit int. So there's the smallest int and the largest int. So int is an instance of bounded. And foldable for container types, but at the moment we have only seen lists as an example. Okay, and normally you have to write instances by hand. So in a later lecture we will see how, if you have a type, how you can make it an instance of one of these classes, or also of classes that you yourself define. But for some important classes, there's support built into GHC, or even, I think that's not even GHC, that's like specified in the language definition already, that for certain types there has to be an automatic way to derive it. And eq and show are examples of that. Foldable is not, but GHC has an extension to also automatically derive foldable. So if we go to our this chain prime type, for example, or also the original one, we can write deriving, it's another keyword, and then we can list, for example, show eq. And now the compiler automatically makes this class, this type an instance of these classes. So now if I reload and ask again for chain 1, I no longer get an error message. Now I get a string representation of chain 1, this block, Genesis block 2. This is now because now it is an instance of show. And now I can also use like the equality compare, the equal, because it's also an instance of eq. So now I can do that. Earlier I would have gotten an error message that chain is not an instance of eq. And on the slides there's also foldable. And if I do foldable here, I get an error that cannot derive instance of the form foldable. And that is, so that is like not built into the language directly, but GHC, like for so many things, has an extension for that. You can activate it. The syntax for extensions is a bit weird, but it's like this. This is a so-called pragma. It's these curly braces minus hash, and then there are various different types of pragmas. You can also give compiler options and so on, or enable certain warnings or disable certain warnings. But one of the things you can do is you can activate extensions, language extensions. And one of those extensions is derive foldable. And that means that now it can automatically derive foldable, but there's an error in the slides, obviously, because I think it needs to be functor. What's the problem? Oh, no, sorry. This, forgive me, that was bullshit, because this is not foldable. The other one, the chain prime, that is foldable. Let me do the same here. Show eq, and now here I can also do foldable. Foldable type always needs exactly one type parameter. The original chain type is not a container type. Never mind. Okay, so now I can write foldable there in the deriving clause as well. And that means we saw earlier that, for example, length is defined for any foldable container. So now the length function magically will also work for chain prime. So now if I reload, so let's take something, whatever, block Genesis block, I don't know, 5, 3. So first of all, we get to all these irritating error messages later, but okay. So first of all, it's showable now. And now I can also ask for the length. And it computes the length. So because we earlier saw the type of length was, it takes any foldable container and computes the length. So now I made chain prime instance of foldable, and now the length function suddenly works for it as well. But yeah, we will go into all these type classes. I think there's a whole lecture dedicated to type classes. But I mean, this is special cases that you can automatically derive it. So normally you, in most cases, or often you have to write instances by hand, and we will see how you can do that. Okay, so that's that. That's like the very basics, and now we come to like the two, remember I had the list of properties that Haskell has, and the two last ones were in red because they make Haskell really stand apart from other languages. And one of them is so-called explicit effects. And we have pure functions. A function is pure if the result only depends on the input. And there are no side effects. And so that's like in a mathematical function. If in mathematics, a function maps inputs to outputs. If you give it the same input twice, you get the same output twice. In programming languages, that is not necessarily the case. I mean, you could have a Java or whatever, yeah, let's say Java function that takes an int and produces an int, but in the implementation of the function, it, I don't know, goes on the internet and reads the database and looks up some number in some database and returns that number. And if I call this function, this Java function twice with the same input, in the meantime, the content of the database could have changed and you get two different results. So in other programming languages, you can't know that each time you call a function with the same value, you get the same result. In Haskell, you always get the same result. I mean, I'm lying a little bit, but in principle, that's the general idea. And that is called pure. And if you want something that's not pure, if you want a side, I mean, I think originally, like in the 1980s, when Haskell was first founded, when this was it. And you couldn't have any side effects, full stop. But of course, a function without side effects, I mean, that's just a very expensive way to build a heater for a room, because, I mean, you can't observe anything. I mean, you know, if you want it to do anything useful, it must have an influence on the world. I mean, it must print a result to the screen or send them, do something on the network or write something to a database. If it has no way to communicate with the world or change something, then it's completely useless. It just heats, I mean, just uses energy and, yeah. So you need side effects. But the point is that, so it's not as if Haskell doesn't have side effects, it's just that in Haskell you can clearly see whether a function does have side effects from the signature. So if you see a Haskell function f of type int to int, you know that the int you get will only depend on the int you put in. If you put in the same int, you get the same int out. If you want something that is able to check a database or go on the internet or print something or read something from the keyboard, you don't have the result type int any longer. Instead, you have the result type IO int. And this, I mean, I think we often call it an action. It's an action that returns an int. So you can think of it as a recipe of steps, and it's still true. I mean, this is an important point somehow that also took me quite a while to understand. So it's still true that any function in Haskell, same input, you get the same output. This is also true for G. But the output in this case is like a recipe. So putting in the same int, you get the same recipe out. But then the Haskell runtime will take this recipe and actually execute it. And then the result of the execution can be different. So for example, in this example earlier, let's say G takes an int, and the recipe it returns is go to this database, look up in this table, in some table, look up the number there, and then add it to the input number and return. So this recipe is fixed. That only depends on the input number. That doesn't change, it has nothing to do with the database. But if you then actually execute the recipe, then the result then depends on the value in the database at that time. And in Haskell itself, there is no way to execute these recipes. So that's only the Haskell runtime that does that. So only at the very top level, if you have, we will see how you write programs in Haskell, like executables. And they have like a main entrance function. And only when you compile the function and then execute it, then, this IO recipe will actually be executed. But that's like something external to Haskell. So from inside the Haskell program, you can't. And the second thing, if you don't compile a program and execute it, GHCI also does that. It also executes so-called IO actions. So for example, one IO action is called read file. It takes this file path and returns an IO string. And file path, if we ask for file path, this is just a synonym for string. So let's see. I have, for example, this high YAML file, so I could do read file high YAML. And now this actually gets executed. So what read file does is it takes a path to a file on the system and then returns the IO action that will read that file, and the result string will be the content of the file. And because I'm now in GHCI, it actually gets executed. So this line here is the string that, that's the content of this hi.yaml file. Right. And did that. And now let's say you want to write a function that, given a file path, computes the length of a file. So you can't do this. If we try that, length, then we get an error. And the reason is that the types just don't fit. Because if we recall, read file returns something of type IO string, but length takes some container and returns an int. But string is a container, but IO string is something else. It's a different type. So this just doesn't fit. So therefore, I can't apply length to IO string. Nevertheless, of course, in Haskell, there is a way to compute the length of a file, but you can't just apply length to this result. There is this funny operator, and with that, we actually get the effect that we expect. So if I do this instead, then I learn that there are 19 characters in this file. And I think it's no use going into this now. because we will have a whole lecture dedicated to I/O. But there are various operators that allow you to take simple I/O actions and combine them to more complex I/O actions. So they are like everything you would expect is of course available in Haskell, like reading files, reading from the keyboard, writing to the screen. I mean, this one I could show. So that one, for example, is there's put str and put str line. So I can do this, and the side effect of this put string line is it puts the given string onto the screen. So I mean, all these things you would expect: networking, database, I mean, yeah, sockets, reading from the keyboard, writing to the screen, reading from file, writing to file. All of that, of course, is available. But often you want to do many more complex things, right? Read from different files, write something, ask the user, write something on the screen, asking for keyboard input. So we have like lots of, I mean, a very complicated AI action that you want. And there are these operators, and I really think I shouldn't go into them now, that allow you to take like simple I/O actions and combine them to more complex ones. So you can build up very complex programs from very simple building blocks using such operators. Okay. So the point is that you will see on this I/O type, whenever this I/O type appears in the signature of a function, you know there can be side effects. And so the type system or the signatures already guarantee, or you can immediately at one glance see whether a function can potentially have side effects or not. And the second point is we cannot lie about this, and this is not true. I mean, there is a way, like an escape hatch, you can lie about this, but you shouldn't. But there is a way to, I mean, for library authors, so sometimes it makes sense to lie about this. But in general, not. And I mean, things that are programs that have I/O result types, they are called effectful programs because they can have effects on the world, and they have stronger requirements than non-effectful ones, and that encourages a style. So it's always a bit of a hassle if you have I/O involved, because the types become, I mean, we saw with the length, you need this funny operator if you want to compute the length of a file. So that pushes programmers in the direction that you try to separate your side effecting code from the pure code. So typically or ideally a Haskell program, there is like a small part that does AI, like typically to read input data, like from a file, for example. Then you have the main part, all the logic is like pure, has nothing to do with I/O. And then there's a small part that presents the results to the user, which is again I/O. So I mean, this way of doing things encourages programmers to separate like the logic, the pure core of the program from the periphery where you have to communicate with the outside world. Right, so that's this effectful thing that makes Haskell very special, because even in other, yes, a question?
What does it mean to lie about this?
It means there is a function, let's see, do you know where that is? Unsafe from I/O? GH?
Is it in the base I/O? Because it's part of the base library.
Nope. Just a second.
Maybe in GHC I/O.
Yeah, maybe. It's something unsafe.
So while Lars look at that, like the whole idea of having that I/O is that when you don't have the I/O, you can be sure that it will work as you think it will. It won't make any funny stuff, won't connect to the database, won't do anything weird. So as soon as you start to running I/O code without that marker, you cannot trust your code anymore. It's just the same as using just like JavaScript or whatever that can do side effects again. So we lose that advantage. So that's why you shouldn't, and the people that actually use Unsafe I/O are people that like write like advanced library with trying to like get a high level of performance, and they are experts. And but then at the end of the day, the interface that they give to you are safe because they are like managing, they are taking like care of doing that well. You can go like virtually your entire career without using unsafe I/O.
I think I've never used it. Right, so I mean, one way to think of this I/O, I mean, actually it's just a type like any other type more or less. But I mean, you can think of it as a marker that marks something as dirty, or I mean, dirty sounds so negative, but like side effect having. So whenever you see I/O somewhere, it means that code can it's not clear what the outcome will be. It depends on database, networking, internet, file system, and so on. And if you don't have an I/O, you can be sure normally that, so this I/O is like, once the I/O is there, you can't get rid of it again. So once something has an I/O type, there's no way to get rid of that. So once your code is marked as having a side effect, then whatever you do, when you use that, it again has a side effect. So I mean, once it's dirty, it's dirty. You can't get it clean again. Except if you use something like unsafe perform I/O. So that is this type I/O A to A. So this is what we mean by lying. So if you have a function that should have result type I/O string, if you apply unsafe perform I/O to it, then the I/O is gone and you don't see it anymore. So if I do like unsafe perform I/O of read file hi YAML and ask for the type of this, then it tells me it's a string. So no I/O string, it's just a string. But this is lying because I mean, if I do this, I mean, I get the right, but now if I now use the editor and actually edit this file and do the same thing again, why doesn't it?
It is.
Oh, it is.
It's the SD.
Oh, the S is there, yes. So see, now I did the same thing again of type string, and I get a different result. And that should never happen. I mean, that's this referential integrity. So type string should mean this term should always give the same result. And it doesn't in this case, because now suddenly I have this S. And that's because I was lying about it using this unsafe perform I/O. But they make very sure that, I mean, to make it clear that you shouldn't. I mean, that's why it's called unsafe perform I/O. Because if you use that, you must really know what you're doing. Because normally it's a bad idea.
Also, like if Lars by any chance like names that function, and then you don't know the implementation of the function, but he gives it use default username to that function, and you just get this default username function that returns a string, and you assume it's a constant value that will never change. You use it like that, but then for some weird reason, the implementation use this answer perform I/O, then it starts changing, and then you get a different user for some reason, and you don't understand why. It's because there's no I/O in there. As soon as you see the I/O, you see, okay, there's something fishy inside this. I need to know what the side effect is doing.
Yes. It's normally very powerful that you can't do that, or you shouldn't do that. And there are also ways, there's something called safe Haskell, I think. So there is another GHD extension that you can activate, and then unsafe perform I/O isn't allowed anymore. So then then you really can't lie about it anymore. And that is important because, for example, it allows all sorts of refactorings. So I mean, normally in Haskell, if I have something like this of type string, and whenever I see this anywhere in my source code, I can replace it. So I can do optimizations, for example. I can, if I have like one expression and the exact same expression somewhere else, and it's like it takes long to compute, I can just compute it once and then just put the result everywhere where I see this expression. And I'm guaranteed that that is fine, that I don't change the meaning of the program when I do that. But this all goes out of the window if once you have something like unsafe perform I/O. So in Haskell is, I mean, it's very powerful. You can do very powerful refactorings, for example, because you can rely on these properties. And in other languages, you can't. I mean, in Java, it can make a big difference to replace a function by its definition. But in Haskell, not. It should never make a difference. You can always freely inline code or extract like duplicate code into its own function, and it doesn't change the meaning. And that's only because of this.
The compiler also uses that knowledge to
Exactly.
automatically optimize all your code.
Yes, the compiler, because of this, the compiler can do much more aggressive optimizations than in other languages, because it just assumes that, I mean, it can freely exchange expressions for the definitions inline and so on, and it does that like aggressively over modules, even above, I mean, across module boundaries and.
Yeah.
Right. The second big thing, the last on this list of the items that make Haskell special, so one is this effect system. So that's really very unusual. So it's, I mean, Haskell, except for some experimental languages like Acta or PureScript, or, I mean, this really the only language I'm aware of that has that. I mean, even other functional languages like Clojure, or I don't know what's a good example, or Camel, for example. They don't have this. So you can have side effects in the code. So Haskell is really the only sort of mainstream language that does that. And lazy evaluation is another thing. I mean, people are like, some people think it's maybe not so wonderful that Haskell does that, but it's what it is. So as an example, let's write another function. I mean, until now, we only had functions that take an existing chain and compute something with it. Let's write a function that can actually build a chain of a given length. So I want to write a function that builds me a chain of a given length. Okay, build n. And, okay, I'm not sure how was it done on the slides with if. Okay. So there is an if in Haskell. So it takes a Boolean condition and then an else branch. So if n is less than 0, then the result will just be the genesis block, and else, and I can like format it nicer. I normally always use 4 spaces, but that's also up to personal taste, and most people use 2, I think. And else I just use the block constructor and recursively call my build function on one less, and for example, take n as payload. Let's try it out. So build, I don't know, 5, and I get a chain of length 5 with the payload 0, 1, 2, 3, 4, 5. So that's just as an aside. And now there's one thing, is it T? Set, hang on, I always forget. There's one setting where you can show timing. Type. Do you know?
You can grab the output. I know you're in.
No, I'm in. Yeah. Just give me 1 second. I'll just make it. Why can't I make the? Oh, yes. Sorry, I can't read this. It's also not important, but sometimes it's useful. There it is.
You can get out of JC.
Here it is, plus S. Okay. So now let's make it. How big was it? Is that big enough? The font? Yeah? Okay.
Yeah.
Right, so if I do plus set, colon set plus m, so now if I do something, I don't just get the result. Why doesn't it work? Wasn't it plus m?
It wasn't S,
Oh, S, right, S, sorry. Right, so now I don't just get the result, I also get some information how long it took and how much memory it consumed. Right, and I mean, it takes 0.00 seconds, but let's, instead of 5, do 10 million. And I don't want to display the result because that would like fill millions of screens. So let's instead do the length of this. Sorry, that we haven't seen that yet. Like this. Yeah. What was now? Oh, yeah. It's because I must use this chain length. Okay. So this should take a while. So it will now construct, okay. So it built a chain of 10 million blocks and then computes the length. And the result, I mean, because of our implemented is 10 million and 1. I mean, we could change it doesn't matter. The point is it takes more than 5 seconds. But now let's look at this. Has block prop even. So how long do you think will this take? Longer, or will it be faster, or will it be slower than the length? Or about the same? Sorry? Faster? Okay. 0 seconds. And that is also special to Haskell. In almost every other language, it would take basically the same time. Because in any other language, when you have something like this, so a function applied to an argument, most other languages first compute the arguments. So no matter what you write here, any other language would first execute this, construct the list with 10 million elements, and once that is computed, it would apply those computed arguments to the function. And that's called eager evaluation, and that's what you are all used to. So if you have a function with arguments, then the interpreter or compiler will first evaluate the arguments fully, and then plug them into the function, and then evaluate the function. And Haskell has something that's called lazy evaluation. So Haskell doesn't do that. Haskell only does what it needs to do in order to give you the answer. And in this case, as we will see on the slides, it doesn't need the whole stupid blockchain with 10 million elements. It only needs like the first 2. So the way Haskell does it, okay, this is this, it takes long, and now this is much quicker, and why? Right. So if we do this again, what we did earlier when I explained how something was evaluated, so we can just replace something with its definition. So we want to see has block prop even build 10 million. So we put in the definition of build. So it's just this, what we saw. And okay, how is an if statement evaluated? Well, you evaluate the Boolean condition, and if it's true, you evaluate the first branch, and if it's false, you evaluate the second. So in this case, so we first evaluate this condition, 10 million less than or equal 0, which is false. So that means in order to evaluate this if thing, we must evaluate the second branch, the false branch, the else branch. So this reduces to this. Right, and now what was the definition of even, of has block prop? We check in the case of the block constructor, we first check whether the payload has this property or recursively the rest of the blockchain has that property. So this reduces to this. So we check whether this is even or whether recursively this is even. Now this is even. So we have true or this recursive call that would take forever because this is, and this is just true. Because of the way or is defined, it doesn't matter what the second argument is, right? If we know, if we have like logical or, and we already know the first argument is true, then it doesn't matter what the second is, we know the result is true. So we never have to build, because in this chain, the very first payload is already an even number. We don't care what the other 9,999,999 blocks payloads are, because we already found an even one. And we can immediately say true without doing any work, or only less tiny work, only the very first step. And as I said, if you try this in any other language, it will take more or less exactly as long as computing the length of the thing, because it has to first construct the whole blockchain before it plugs into, And like a bit more formally, so if you have an expression, like with a function, and then arguments to it, then every other language first evaluates the arguments, and when all arguments to a function are evaluated, then it gives you the result. Then it plugs them into, then it evaluates the function. But in Haskell it's different, it starts from the out and goes in. So, so expressions are only evaluated when needed. And that means you can even have infinite things. Like in Haskell you can even have a list of infinite length. If you never look at it, or if you only look at like a finite part of it. So for example, we could have something just briefly. Let's say, I don't know, should I? I could say, yeah, why not? Let's see. Like, let's call it infinite. It's, let's say, a list of ints. And I just define it as infinite. Let's say a list of int that starts at a given int. And that's just this given int, and then recursively infinite n plus 1. So this builds an infinite list, right? Because it has no base case. If, for example, if I take infinite 3, then infinite 3 is the list that starts with 3 and the tail is infinite 4. So it's 3 and then 4 and 5 and 6 and goes on and on. So if I would now type infinite 3, then that will be bad. I mean, it's not the end of the world, but then I get like it doesn't stop because it's an infinite list. So I have to interrupt it with Control C. But if I ask, we saw this anything earlier that checks whether there's an element of with a certain property, and if I, for example, say any odd infinite, whatever, what did I say for? I don't know. Then it says true. So it doesn't crash. And it doesn't have to compute infinitely many elements. Because in order to check whether there's an odd element, it checks. So 4 is not odd. It checks the next one, 5 is odd, yoo-hoo. And 6 to infinity, it never needs to touch, because it knows its answer without looking at the rest. And that allows for very powerful programming techniques and like modularization. So for example, often you have something called, I don't know what it's called, but generate and check. So let's say you are looking for a solution to a problem, and you have like infinitely many possible solutions, like it's infinite configuration space. And then you have a function that checks, given a solution, you check whether that is a valid solution. So in Haskell, you can basically split that problem into two parts. One that generates all solutions, even if it's infinitely many, and one that checks a given solution, and you just plop them together. So you generate a list, an infinite list of solutions, and then check one by one until you find a good one. And in Haskell, that just works. And in other languages, it wouldn't. So in other languages, you would somehow need to coordinate the two, that they are in sync, like generate a solution, check it, generate the next one, check it. And this, this thing is very powerful in Haskell and allows very neat things sometimes. And that's called lazy evaluation, because it's lazy, it only evaluates what it needs in order to make progress. If it doesn't need something to give the final answer, it doesn't compute it. So that's very cool. And it also means that you can, for example, this logical OR in a lot of languages. In most languages, if you have like logical OR, it behaves like in Haskell, that if you get a true for the first argument, it never looks at the second one. But in those other languages, that is specially built in. So a programmer, you couldn't implement a JavaScript function that has that behavior. It's like built into the interpreter in JavaScript. It's special. It's not how the language normally works. There's special treatment for certain cases. In Haskell, because of the laziness, or it's just a library function. It's defined in the prelude. There's nothing special about it. It's just this laziness in action. So that's one powerful thing. You can build your own control. I mean, things that in other languages need special treatment, like if then else, that you only evaluate the right branch. If your condition is true, you evaluate the first branch. If it's false, the second one. You don't need to evaluate both. That is like a special thing in other languages where they needed to do a special effort to build that into the compiler. In Haskell, it's just normal behavior. And you can build your own control flow constructs like that. But of course, there's always a price to pay. And in this case, it's sometimes difficult in Haskell to discuss, what's the word? Yeah, reason about performance. So given a Haskell program, it can be difficult to say how long it will run, because this lazy evaluation makes it more difficult to understand in which order things are evaluated, so it's much more complicated. So with the standard eager evaluation, it's much easier to estimate how long a program will run. So in particular, for example, for like hardware programming, like on integrated circuits and so on, Haskell would be a very bad choice, because they often have this real-time requirements, so we must know exactly how long a program will run. And that doesn't go well with Haskell. But it is very cool for a high-level thing. So now we're almost done, so just summary. So higher order functions like this has block prop, and the built-in one, or the predefined ones we saw, filter and map. That's something that basically any language that calls itself functional has that. And these days even JavaScript has like higher order functions, filter and map and so on. Polymorphism, so that you write one function that works for many different types, like you can with the length function compute the length of a string, but also length of a list of integer. That's also pretty common these days. And a lot of languages have that. Sometimes it's called generics, or in C++ it's called templates, but I mean, many languages have that. Type classes are relatively unique to Haskell, but you can achieve basically the same effect in other languages with something that has different names. They don't call it type class, but it's an interface or a trait or something. But explicit effects and lazy evaluation make Haskell truly special. And I mean, as I said, there are some experimental languages like Acta or PureScript or, that also have that, but they are basically Haskell, and they are written in Haskell. But I mean, Haskell is the only like common or mainstream language that has that. So that makes it really different, not difficult, different. Right, and that was the lecture. And then tomorrow, we'll talk more about how to define, I mean, this was now just like a very rapid thing of covering a lot of things. So of course, we will look at all of that in more detail. And we saw one example of or two examples of how to define data types, so we will see more. And I alluded to this thing that the definition of the data type was very similar to the shape of the functions we wrote on that data type. So we had the two constructors, and we normally had two equations. So we will see many more examples of that. And that is called type-directed programming. So somehow the types that you operate on in your functions somehow like guide you how you should structure your functions. So if you have a type with two constructors, normally you end up with a function with two equations. So that's like tomorrow or in the next days. But now maybe Robertino can take over.
10 minutes.
And just practical, he needs the microphone, I suppose? No. Okay. Should I switch off my laptop? Probably. Yes, yes. If you want to plug yourself in, by all means.
Thank you.
couldn't I
Amen.
do that?
Ah, because I'm fancy. What's going on?
Are you plugged in?
Yep.
With the
And
HDMI thing?
it changed the. Nice. Okay, everyone. So this is the repository. So here we have like the lectures, the examples the last we're going to go through, the actual like the outline, everything. So not sure if you can read. No, the URL is completely impossible to read. But still, like we will share it in the Discord channel, but just so everybody can see it now. This is IOG Edu Key 2023 Cardano Dev 2023. So here's the repo, and let's go here. So there are exercises, homeworks, tests, etc. They all work the same. We have here like a quick overview of what we're going to cover each week, and here we have what you need to actually do the exercises. So we need the GLC, the compiler. We need this library to build everything. We need like an editor and the Haskell language server, etc. So there's a bit of setup, but we already prepared several ways, easy ways that you can do this. So you have the option to use a remote development environment. That the only thing you need to do is to go here to the Gitpod website, and it's gitpod.io. We're going to share the link in Discord. So here you just click here if you have Chrome, and here if you have Firefox, and as soon as you install the extension in your browser, you will get this nice button here that says Gitpod close in your repo. So you click there, and it will open a VS Code with everything pre-installed, ready to go in the browser. It will run on Gitpod servers, so you don't have to have like a fast computer or anything. It just work. That's one of the options. You can use all the options interchangeably. There's no difference. All the environments are the same. Another option is that every exercise you will have, like for example, if we go here to the first week, the lectures of the first week, you have this button for each assignment. You click here, you will get access to a private repository that will be linked to your GitHub account, and when you like finish the homework and push the changes, we will be able to see them and like give you feedback, etc. So while doing this, you can still use Gitpod, but if you want to like do it locally, you can. Oh god, this is. Let's see this one. So you have to have, if you want to run it locally, there's no need, but that's an option. If you want to run it locally, you need to have Docker Desktop installed in your computer and the latest version of VS Code, or the previous one, but I think the latest will be better. And if you have those two things, as soon as you open the repository in VS Code, you will get a notification that I'm going to show you right now. But first, I want to show you how to like actually use the repo. and you click in that notification, and you will again you will get like a Docker image that will run it automatically, will install everything on your computer, and it will open the workspace here. So right now I'm inside the workspace. The workspace Lars was a bit ago. So here you have the actual exercises. The exercises of the first day are like pretty simple. You have to kind of like follow the same trail Lars did. As you can see here, we have the same definitions Lars went through. And at some point here you have, for example, the length chain function that Lars defined. And we have this error to do implement length chain. So here you have to like delete all this line and put the proper definition on the length chain and keep doing that. How do you know that you did it the right way? We're going to have a lesson about this, but just so you can start working on it. The only thing you need to do is to run cabal test, and everything is set up in a way that it will test. Here you can see like I tested 67 examples and I have 67 failures because I didn't implement anything yet. So while you are completing each task, you can rerun this test and make sure that it passes the test. So you are pretty sure that everything is correctly implemented. Maybe it's not like the nicest, the best, it doesn't matter, it works, and we will try to help you write cleaner code once you feel more comfortable writing correct code. But yes, you can start like using this right off the bat. Remember, it's just cabal test. The first time you run it, it will like build all the libraries, like prepare everything, and then run the tests. And of course, you can, if you scroll up a bit, you can actually see the test. This is the 67th. Let's go to the first ones, the one we were talking about. 11, longer chain, blah, blah, blah. Length chain, error called, blah, blah, blah. Where's the to do? Here, to do, implement length chain. So you will like get in, if you try to implement it the wrong way, you will get a personalized message. So that's it. That's everything you need to do. Like change this file. Inside the source. This is the only file inside the source. Change it, save it, cabal test. Keep doing that. And once you finish everything, you just push the 10. Or if you cannot finish everything, it's okay. You just push whatever you managed to do. That's it. Usually these are just in the day, like for the next day, but I didn't put a deadline on this, so like you can like do it tomorrow or the next day, because we're a bit tighter on time than usual. So yeah, that's it. So to make sure that you have the development environment, and as soon as you going to reload the window, so imagine I'm opening this for the first time. I will get, close this and save, code. Here I open this for the first time, and here I say this folder contains a dead container. Do you want to reopen the folder? Yes, reopen the folder, and that's it. Now you have to wait for the setup. It will open the files, everything. You can start working. And that's pretty much it. Any questions about it, or about whatever anything that Lars said? So we can, we are able, like we are available for you. Yeah.
The content is being shared as screen. You will be shared in Discord.
Yes, and there's also like in here for the setup, there's instructions here, and also the lectures will be like published in the same repository, so everything will be there.
And today I didn't do anything that wasn't on the slides, I think. But
No.
sometimes if I get a question or so, I may come up with an example that's not on the slides, and then these examples would also be in the GitHub repo later.
Yeah. So now we're going to test you in the actual slides. So I'm not sure if you want to upload them now or tomorrow, so they don't
But
have
the
them.
slides, aren't they uploaded yet?
I'm not sure. No, but we can upload them like
Yeah, we can.
in
do
10
that.
minutes.
Yes.
So yeah, any other questions? We have these folders of examples also, but this one don't have anything yet because like there will be the examples that are uses during the course. So as every lecture that is made is being uploaded at the time, and also we have this reduced. We hidden most of the outline because the idea is that we have everything like ready to go, but we want to update, like change the outline based of like what like your progress, and if it's too easy we can do more, if it's too hard we can do less. So we're going to like keep changing based on your feedback and how you complete the assignments.
Did we say that tomorrow we are here an hour earlier for people that
Yeah, we'll be here earlier. So and if anyone wants to come earlier, we'll be here.
like 1 hour? we said,
1
right?
hour or yeah, 1 hour.
I don't
If
know.
someone wants to come earlier, we can arrange that too. So I can come earlier, or
Yeah,
three
you
of
can
us
also, I mean, yeah, you can also contact us on Discord, of course.
as well. Yeah.
Yes.
So that's it. Any other questions?